All right, so let's start. So today's topic is the path integral formulation of quantum mechanics. So before we start to discuss the nitty-gritty of the path integral, we need to revisit the idea of a propagator. So consider the time evolution operator. So the time evolution operator for a system, which the Hamiltonian is time independent, that's given by u t minus t naught, and it has the form of exponential of, there should be a minus I divided by h bar, the Hamiltonian operator times t minus t0, okay? So this is clear, right?
Yes, sir.
Okay. So the right-hand side is actually a shorthand for a formal power series, which has the form, it's an infinite power series. So this is times, okay? It's not a function. So this factor raised to the power n divided by n factorial. And u is called the time evolution operator, but it's also known as the propagator. And what does u do? If you have a state at some particular time, say at t0, then when you apply u onto that state, it evolves that state to a state in the future. And that's why it's called the time evolution operator. So as I said, the time evolution operator is also called the propagator because it propagates the system. It has many names, but usually propagator is, when people say propagator, people mean a particular representation of the time evolution operator. In particular, the position, the coordinate representation. So if you take, say, the eigenbasis of the position operator, and you sandwich the time evolution operator in between, then what you get is, you get a complex number, right? This is no longer an operator because you've sandwiched it between two states. So let's call this k, and k is a function of xt as well as x prime t0 or t. Well, we could have called it, let's call it, instead of t0, let's call it t prime. We'll be switching some notation here and there. Okay, so the same information is contained in both of these forms. Okay, the same information is contained in both, forms. And U is just it's an abstract representation, right? Psi of t is ut minus t0. Psi of t0. Again, I'm reverting back to my original notation. Sorry about that. So now if I take, so this is an abstract vector. This is another abstract vector, and it's an abstract linear operator. But we can look at it at a certain basis. Suppose we're looking at it in the position basis. So if I look at it in the position basis, then I have on this side u t minus t naught psi of t0. To bring the right-hand side to get this guy on the right-hand side, what do we have to do? Can someone tell me?
Spectral decomposition.
Exactly. We do the spectral decomposition of identity, right? So we get t minus t naught. Let me make some space here. And integrate over, d cubed x. So here we have x, dqx prime. So we have x prime psi of t0. And thus we see that we get the expression that the wave function at some time t is given by the volume integral of the propagator whose arguments, one argument is at the final time and spatial position, and the other argument is integrate over all the initial positions at the initial time. Okay. So again, sorry for t prime and t0. It should be t0. Yeah. Okay. So is it clear that the two things are equivalent?
Yes, sir.
So this equation is just this equation in a particular basis. In the position basis. Okay. So what does the propagator actually mean? What is its significance? Well, it's related to causality, really. So this is our next topic, causality and the propagator. So the interpretation of the propagator is causality, and it can be seen from this equation. So what's happening here is that we are given some initial condition of our system. So at some time, at some initial time, t equals to t naught, we are given the state, or the initial state, let's call it, the initial state of the system. And it's given in terms of the wave function over all of space. Okay? And the problem is, how do we find the final state of the system? Of course, this is physics. This is the central question of physics. And the Answer is true. If we know the propagator, then we basically find it. It propagates the initial information to a final information here. Okay. So another interpretation, a more particular interpretation of the propagator is that the propagator say k xt comma x prime t prime is the evolution of a wave function which describes a particle localized at the position x prime at time t prime. Okay. So what I'm saying is that suppose that you have your time in that direction, space in that direction, and this is say t prime, the original, and you had some point called x prime, and you had the wave function was basically localized here. So it was kind of a delta function, wave function. Then, what would happen is that as time progresses, the wave function would spread out, and then it would have a much more bigger support at time t, right? That's what we expect. So this is and this wave function is k. Okay, so this is easy to show. What we do is that we say that our initial wave function, which was psi at x prime t prime, that was given by let's call it psi 0, the initial position, and that was isolated at x prime. Okay, so this is x0. Then according to our formula, the wave function at the later time is given by d cubed x0 k xt x0 t0, say, or t prime. Sorry, I keep on doing this. I should really commit to something, but yeah. Times the original wave function. But the original wave function is this thing. So we multiply it by delta cubed x0 minus x prime. And now if I do the integral using the delta function, this just becomes k. Psi of x at t becomes k at xt x prime t0. Okay? Any questions?
Sir, like, what's the difference between del x naught and del x prime? Are they the same thing? I don't think so. But
well, del x naught is a variable. The x prime is a particular value of that variable.
Oh, okay, got it. Like, I was getting confused with all the notations, like x, then x prime, x naught.
And I'm not being very careful, so you're completely justified in getting confused. So, yeah, del x naught is basically the coordinate for the space-time, for space at t prime, and x prime is just one particular point on that manifold.
Yeah, got it. Thank you.
So in a certain sense, what the propagator represents is, K represents, the effect that propagates due to a unit source. Okay. And you can show that, and this is something I'm going to leave as an exercise for now. It's very instructive to show. You can show that the propagator solves, that the propagator solves, with the boundary condition being, if you say, if this is x and this is t, this is x prime and this is t. So if the two t's are the same, then this should be delta, right? Basically, it should be the identity. Because that's exactly what we showed before. This is prime. So with the boundary condition that the propagator solves the wave equation with source. With source. And that equation is the Schrodinger wave equation, wave operator, that's IH bar d by dt plus h squared by 2m gradient squared minus the potential energy acting on the propagator. Oh, and this is the first. So these, derivative terms are acting on the first arguments. Okay. So this is going to be equal to delta cubed x minus x prime and delta t minus t prime. Okay. So this is an important property of all propagators. So in mathematics literature, so in some sense, or in a precise sense, the propagator is the inverse of the wave operator. Right? So if I look at this equation and express it as a matrix equation, then I have some wave operator, say call it the Schrodinger wave operator, d of s, that acting on the propagator gives you the identity, right? So if I think of this as an infinite dimensional matrix, this is the inverse, right? So the propagator is the inverse of the wave operator. And in mathematics literature, the propagator is called a Green's function. Okay, because some guy called Green had invented it in the 19th century. So when Feynman was developing his quantum electrodynamics and his version of quantum mechanics, he confided what he was trying to do to to Freeman Dyson. And Freeman Dyson told him, oh, what you're doing here, these are called Green's functions. You should look at mathematics literature and read up about it. And Feynman refused to do that. He didn't want to be influenced by what was already known by him. He preferred to invent it himself. Okay, so any questions so far?